So in this video we're going to look at finding the domain of a function of two variables. So here it says determine the domain of f of xy equals 2x over y minus x squared. And what we want to recognize is when we had a function of a single variable, we had y equal f of x, and x was the input. So you input a real number and then the output is some real number when we're working with real valued functions. But now that we have a function of two variables, we're going to have functions that look like z equals f of xy. So we're going to be inputting ordered pairs. We're going to have ordered pair inputs, and then we're going to have real valued outputs, which is why we've been working now in a three-dimensional coordinate system recently. And the idea is when we find the domain, we just are looking for those restrictions that we looked at in pre-calculus. What are the things that you can't plug into the function because it'll cause a division by zero, you'll be taking the square root of a negative, or functions like the natural logarithm that has restricted domains. So we're just looking for those typical restrictions. So in this case, I look at the numerator, and I can do anything I want here in the numerator. This is just a linear function in the numerator. And the domain of 2x actually is negative infinity to infinity, but I want to pay attention to the denominator. And I know that I can't divide by 0, so when I'm looking for the domain, I'm really asking the question, when will y minus x squared equal 0? Because we don't want y minus x squared to be 0, because that would cause a division by 0. So if I solve this for y, I get that y cannot be x squared. And I could actually describe the domain in set notation. I could say the domain is equal to the set of all ordered pairs xy such that y isn't x squared. And if we think about this graphically, the domain is the set of all ordered pairs that we are allowed to input into the function f and generate a legitimate output. So the domain is living in the xy plane where our ordered pairs xy live. So if we say y cannot be x squared, we're saying that we can't use any ordered pair on this parabola. This is the parabola y equals x squared. So we're really identifying that y equals x squared is the thing that we can't use. I can use any ordered pair in the plane, any ordered pair in the xy plane other than that parabola. And again, if this is y and x, I can extrude that z-axis out. So the points that we plot will be above or below, as necessary, the xy plane, but the parabolic cylinder y equals x squared won't have any outputs on it. So looking at another example, I have f of xy equals x times the natural log of y. So putting anything in that we want for x, putting in any real number for x isn't going to cause any issues, but the natural log function has a restriction on it. We can only put positive numbers into the natural log function. So here we see that y has to be greater than 0 so that we have positive numbers. So if we're thinking about the set of ordered pairs in the xy plane that we would be allowed to input into our function, we would have any y greater than 0. But y equals 0 is just the x-axis. So what we're saying is don't include the x-axis, because on the x-axis y is equal to 0. So here's the x-axis as a boundary. The x-axis is the line y equals 0. And if y is greater than 0, we're saying we can put in any ordered pair we want that is above the x-axis. And again, we would be extruding the z-axis and plotting our outputs using the positive x and negative x z-axis. So one more example. So here we have a square root function. So here's another common restriction. We want to know what ordered pairs can we input into the function so that things are legit. Well, the square root function, to get real valued outputs, we have to have non-negative numbers input into the square root function. So we know that 4 minus x squared, said x squared and wrote y, 4 minus x squared minus y squared has to be greater than or equal to 0 so that we have non-negative numbers under the radical sign. And then I can rewrite this by adding x squared and y squared to both sides. I can rewrite this as x squared plus y squared. So I see here that 4 is greater than or equal to x squared plus y squared, or equivalently x squared plus y squared is less than or equal to 4. So if we're thinking about the domain, x squared plus y squared equals 4 is just a circle of radius 2 in the xy plane centered at the origin, and we're saying that we have to be less than or equal to 4. So that means that the domain of this function is everything on or inside of this circle in the xy plane, and again that z-axis would be extruded. We could describe this in set notation if we wanted to. We could say the domain is equal to the set of all ordered pairs x and y, such that x squared plus y squared is less than or equal to 4. And I don't think I wrote it in set notation on the previous slide, but we could do that here as well. We could say the domain is the set of all ordered pairs x and y, such that y is greater than 0. So we could describe this in set notation if we needed to. So there's some examples of finding the domain of two variable functions and taking a little bit of a look at the geometry of the resulting domain.